And it's my pleasure to introduce our first speaker, Ursula Michael. Ursula is the Geoscientific Data and Communications Officer at the Geological Survey of South Australia. And Ursula will present the latest work by the GSSA on open standards as a means to deliver data ready for use in data analytics by the exploration industry. Please welcome Ursula.
Thanks, Peter. Good afternoon, everyone. What I want to do today is share with you what the GSSA is doing in the data space to make it easier to access data in an open way. The Department for Energy and Mining's award-winning SARAG application provides access to more than 130 years of geoscientific data curated by the Geological Survey of South Australia. Information derived from government, research sector and industry mineral exploration, delivered in a range of file formats including CSV, Google Earth, KMZ, Esri shapefiles and file geodatabases, map info tab files, and Open Geospatial Consortium or OGC web services. Formats to ensure that this data is interoperable with a range of applications and meets a wide variety of analytical requirements. If you have ventured over the border to download data from another Geological Survey's online portal, you would have discovered that our fellow surveys are delivering the same types of data, but in a different structure, and they are probably using different vocabulary terms. A survey of data scientists revealed that they spend up to 80% of their time preparing data. This includes finding the data, getting the data in the same information in the same fields, ensuring numbers are numbers, text is text, and standardising units of measure and geological terms. Exactly what is required to merge South Australian data with another Geological Survey's data into a single data set. To achieve true interoperability, we need international standards to break down open data jurisdictional silos and to help big data analytics thrive. Open standards make the exchange of data easier as data isn't tied to individual providers or systems. In the 1950s, Malcolm McLean, while sitting in his truck watching cargo being slowly loaded by hand, tied together and stacked unevenly on a ship, came up with an idea that would change the world: the shipping container. It transformed commercial shipping from a costly labour and intensive and inefficient system into a booming industry that radically dropped the cost of transporting goods around the world. Soon after, the ISO Technical Committee for Freight Containers was established in 1961 and has since standardised almost every aspect of containers, from their overall dimensions to how they can be stacked, to the twist locks that fasten them to the ship's decks and truck trailers, to the terminology used to describe them. These standards enable containers to carry their loads safely from ship or aeroplane, from rail to truck, loaded on and off with uniform equipment and processes worldwide, saving time and money. Like the humble shipping container, there are many benefits to be had from moving our data around in standardised ways. International standard protocols for delivering and interacting with data over the web are like the standardised shipping containers that hold and deliver our data. The Open Geospatial Consortium, or OGC, is an international consortium of 530 businesses, government agencies, research organisations and universities driven to make geospatial information and services findable, accessible, interoperable and reusable. OGC has defined the specifications for making maps and data available in open, internationally recognised formats over the web. Web map services for serving maps as images and tiles, web feature services for serving the data about a feature or as a vector, web coverage services for serving data as raster coverages, and catalogue services for the web, which are metadata services to discover data. These services can be consumed using a client such as a web browser or using programming languages like Python or R. Anyone is free to use OGC specifications to create their own processes and applications to visualise and work with these services. We are already seeing developers of traditionally proprietary format applications such as Esri ArcMap and Google Earth, including functionality in their applications to consume OGC web services. The department has been delivering all of our SARAG map layers in interoperable OGC web services for several years, allowing our users to live link with our data and work with our data sets. However, just like shipping containers, web services are a standard way of delivering the data, but they also could contain anything inside. The next necessary step towards interoperability is to start standardising the data within services to add structure and meaning for humans and computers. This will allow us to start automating the unpacking of our data into our data warehouses and web applications, and to merge data seamlessly with data sets from other providers. And the good news for you is there's already a group working on this very thing. The Commission for the Management and Application for Geoscience Information, CGI, is a council of members from geological organisations from around the world who have been tasked with determining the structure of geological data and the geological language to describe data within. CGI working groups are defining the attribute names, order, data types and formats, their logical data relationships, constraints and rules, and what attributes are mandatory or optional. To date, they have officially released 2 data standards. Now also an official OGC standard, GeoSciML Markup Language, or GeoSciML, is the data standard for the exchange of digital geoscientific information. It accommodates representations and descriptions of features typically found on geological maps, as well as being extensible to other geoscience data, such as drilling, sampling, and analytical data. Earth Resources ML is the data standard for mineral occurrences, mines and mining activity. It describes geological characteristics and settings of mineral occurrences, their contained commodities, and their mineral resource and reserve endowments. It is also able to describe mines and mining activities and the production of concentrates, refined product and waste materials. Both standards include a simple representation or light version, flat in structure. These abridged versions are used to deliver simplified views as map services on simple features. More than 100 geoscience vocabularies were identified to support GeoSciML and Earth Resources ML data models, of which more than 50 have been implemented by the CGI Geoscience Terminology Working Group. Standardised vocabularies are lists of names and terms that describe features, properties, quantities, techniques and processes of Earth material. They convey unambiguous meaning for greater understanding and translate terms across different languages. They also enable standardised querying and analysis within and across data sets. Detailed specification documentation and model diagrams are available online, ensuring everyone using the data understands exactly what each attribute is, something that is becoming increasingly important for cross-discipline big data analytics and our expanding community user base. These standards are in use or have been endorsed by data sharing initiatives around the world, including the One Geology Project, the European Inspire Directive, the US Geoscience Information Network, and the Australian Geoscience Information Network and AusGen. Driven by Geoscience Australia, Auscope and the GGIC, data formatted into interoperable standards and delivered by OGC Web Services is already underway here in Australia. The HiLog and National Virtual Core Library project provided a neat and perfect opportunity for the Geological Surveys to implement a standardised GeoSciML Light borehole view service. This is the result of that effort. This is not a data set sitting on Geoscience Australia's web server, but live data coming from each state and territory geological survey, requested simultaneously and styled to present as a national data layer. Some basic querying functionality included in the portal allows this data to be filtered as if it was one data set. For example, all of the drill holes that were drilled in the year 2000. Until now, this joint effort has been limited to implementations of the light versions of the standard. Flat data designed for simple querying and for displaying features as 2D points on polygons on maps. The GSSA has decided to dive in. Here in South Australia, we are leveraging what makes SARIG the award-winning data delivery portal it is, our underlying databases. We don't need to change our internal databases to match the GeoSciML structure, but instead map the standard to our database to format the data at time of delivery. We have started work to map our drill hole rock sample field observations and mapping data sets to the GeoSciML standard and CGI vocabularies. Earlier this year, we released a complex borehole web service, a first for Australia. A complex service is exactly that. It's complex. All of the data relating to a single borehole is encoded as a single feature. It has a nested hierarchy structure, and attributes can contain multiple values, just like in a relational database. If you haven't worked with XML or JSON, this format can look a bit daunting. A single borehole may contain up to 5 different pieces of nested information. The origin position class contains collar geometry and elevation. Where there is downhole survey information available, we have scripted the creation of a 3D line string, which is delivered as a geometry in the shape class. The borehole drilling details class contains header information, metadata about the operator, the storage of the drilled material, and other information relevant to the borehole as a whole. The description of drilling methods and hole diameters down the drilling path is captured in the drilling details class. And finally, the borehole interval, which allows for multiple downhole log types for a single borehole. Currently, our service includes stratigraphic logs and MagSUS and specific gravity measurements. And we hope to expand this to include a full composite of available downhole data, including links to analytical specimens and their results. This service will be the first of many to be built on open data standards. We would like to thank the AuScope Discovery Portal team for their work helping us to deliver our data through the National Virtual Core Library. This assistance has helped us to architect our server-orientated data delivery technology stack to make it easier to deliver more services. And thank you to Geoscience Australia for sharing their expert knowledge and advice on how to implement the standards into our data delivery. We are leveraging these collaborations to help move geoscience data interoperability in Australia forward. South Australia is leading the way in delivering advanced complex web feature services to make semantically interoperable data sets available to the geoscience community, so you might start unlocking the power of a global network of standardised data. These complex web services will deliver South Australian legacy drilling data to the MinEx CRC's Project 7 for maximising the value of data and drilling through cover. Project 7 aims to deliver a single point of access to NDI, or National Drilling Initiative drilling data for all stakeholders, inclusive of data management and delivery systems, geospatial and data analytical tools, and drill target optimisation algorithms. 3D drill hole visualisations in the MinEx portal using the South Australian Complex Borehole Service is already in development, and today I'm able to give you a sneak peek of this work so far. A subsurface look at MSDP10 in 3D with the downhole stratigraphy. Semantic interoperability also provides several opportunities to develop a more efficient big data analysis workflow. The OGC Web Service standardised containers mean that the processes around data retrieval and its local storage may be automated. Catalogue web services of metadata, such as the SARIG Open Data Catalogue, make finding data easier. As they are also a web service, data discovery could be integrated into an automated workflow. Using data delivered in internationally accepted standards like GeoSciML and Earth Resources ML means that the data cleanup has already been done. From here, there is opportunity to automate data quality assessment and filtering to create fit-for-purpose data sets for model ingestion. So whether you are consuming data, generating data, or building the tools to work with data, OGC Web Services and the CGI's GeoSciML, Earth Resources ML, and international vocabularies are free and open for you to use. Thank you.